Since year 2011, Bruel Kjaer leads and participates a project called Predictive Structure Health Monitoring of Wind turbine blades. In the frame of this project, we made a lot of experiments and aiming to develop a technology able to detect and localize damages on wind turbine blades. During this project, we developed technology that actually is able to detect even a 20 centimeter damage on a 34-meter blade with the presence of a realistic noise. In order to demonstrate the technique we developed, we made a small scaled model of wind turbine blade. This model consists of two shells that are connected together with many bolts. Tightening and untightening these bolts, I can mimic any damage or many different damages which can happen on a wind turbine blade. I can put these damages in different locations along the blade, and I can make a different size of the damage. The active method requires that we introduce some mechanical energy into the blade. For this scaled model, we do that by means of a small actuator that looks like that. This is actually an electromagnet with a plunger that hit the blade. For a real wind turbine, we use the bigger version of the actuator. So it's an electromagnet and a plunger. And the other part of equipment is accelerometers mounted on the other side of the blade. There are 7 accelerometers, monoaxial accelerometers on the trailing cage and 7 accelerometers on the leading cage. The second big part of the structure health monitoring system is the algorithm, which actually makes a decision if the blade is undamaged, still undamaged, or damaged. The algorithm is based on comparison between the reference state, which is undamaged state, and the current state. If the current state of the blade is very close to the reference state, then we declare the blade is undamaged. But if the current state and the reference state diverge significantly, then we say that the damage is suspected. First, we need to collect statistics about the reference state. So for that, we will start the actuator, and it will do around 100 hits. During these hits, the signals from accelerometers are measured, and based on these signals, we make a model of the undamaged reference state. So now all the bolts are tightened, and all I need is to start the actuator. Now, after number of hits, the training is over, so we stop the training and make the model. So now the model is being trained using 190 states. So now we will start the test. All bolts are tightened. Starting the test. As expected, the state of the system stays normal, and you can see it's a green rods here saying the blade is undamaged. Let's just wait and give the system several hits to see if any false alarm happen. Now about 40 hits are made in the normal state. You can see that the all detection was correct. All the points are green and the blade is detected as undamaged. So now I'm stopping this test and we'll introduce the damage. Unbolting the first bolt on a trailing cage closest to the tip. So let's try to start the system and see if this damage will be detected. As you can see, damage is detected and the red points shows up here, and the classification algorithm says the damage is detected. After about 40 hits, we still see the damage is detected by the algorithm. So let me stop testing and we'll try to localize the damage. Again, here we can clearly see that the algorithm actually finds the damage, or at least the trained eye can see that the damage is somewhere here. Here you can see the blue is the contour of the blade, so this is the tip and this is the trailing edge, and the damage is actually here. Let me increase the damage, so I will untighten the bolt sitting next to the trailing edge tip bolt and see if the algorithm can detect the progression of the damage. Now after the 40 hits and in this state, can still see the damage is detected and the distance from the normal state is increased. Perhaps it's better seen not on this primary indicator but on the secondary indicator. Here it's definitely seen that the damage is gradually increasing. So again, the damage can be easily located by this indicator. So a trained eye can see that the damage is actually somewhere here, tip trailing edge. Now the third bolt is untightened and I continue the test. Now after about 40 hits, we can still see that the damage is detected and the size indicator is also growing. So you can see there's no damage, one bolt I tightened, the second bolt I tightened, and the third bolt I tightened. So basically you can nicely see the damage is increasing. Again, still the indicator tells us that the damage is here at the tip of the blade and the trailing edge. Now I can see it's increasing towards the root of the blade. Now I'm going to tighten these bolts again and introduce the damage in the next location. As before, I have to start with the training the algorithm for the normal state. So I'll start the training. And let the actuator hit about 100-140 times. Now I'm going to finish the training for the normal state again and generate a model. It will take some time. The model is created, so again I will start the test with the normal state. The algorithm should detect that blade is undamaged. Let's observe the behavior of the algorithm for a number of hits. As expected, during these 40 hits we are testing our normal state. All the points are green, so there's no false alarms, the system works as it should. Now I'm stop the test and we'll unbolt the first bolt and see if the algorithm can detect this damage. Now I introduce damage into the leading edge, somewhere in the middle. Let's start the test with one bolt unbolted. As we can see, the damage is detected. Let me introduce untighten the second bolt and make the damage bigger. And let me start the algorithm and see if this progression will be detected or not. After 40 actuator hits, we can clearly see the damage is still detected and the distance from the normal state has increased. So it is a clear indication that the damage also increased in size. And one more bolt to untighten. The third bolt on leading edge is untightened, and let me start the test. As expected, the distance further increased and could be seen on both indicators. I just finished the test when 3 bolts was gradually untightened at the leading edge of the blade. Location of the bolts are the middle part of the leading edge. You can see that the normal state was tested, was no false alarms. Then the first untightened bolt was also detected, but there was some false negatives. When the second bolt was untightened, then the distance increased significantly, again indicating that the damage grows. There was no false negatives, and again the third bolt was detected as well, and again we can see the distance change quite significantly. The same could be seen in the secondary damage indicator, and distance indicator is here. Regarding location, we can see that the damage is here, and a trained eye can see that the damage basically happening in the leading edge of the blade, somewhere in the middle section of this. It's quite a rough estimate, but believed to be quite useful. This summary of the last test which I made. Here the trailing edge close to the root of the blade was opened. Also I started from untightening one bolt and proceeded with the second, third and the fourth. Again, here we can clearly see the damage was detected. First the normal state was detected, that everything is alright, then the damage was detected, and then gradually the damage was increased. It's not that much seen here in the indicator number 1, but in the secondary indicators it's seen in a better way. Also location could be found, so the damage is happening here in the trailing edge close to the root of the blade.